This video is about ionic bonding. By the end of this video, you should understand ionic bond formation, recognize properties of ionic solids, understand the Born-Haber cycle, and be able to predict the most common ion that an atom will form. Recall that the octet rule tells us that atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. We can use a Lewis symbol to represent the number of valence electrons an atom has, as you can see here. Group 1 elements have 1 valence electron, group 2 have 2, group 3 have 3, and so on up to 8. We can predict what charge an ion will have based on its position on the periodic table. Again, the octet rule tells us that atoms are most stable when they have a full octet of 8 valence electrons, or in the case of hydrogen, helium, lithium, and beryllium, a duet, meaning 2 electrons. Generally speaking, ions will form so that the electron configuration will match that of the nearest noble gas. Take sodium, for example. Here's its electron configuration. Its nearest noble gas on the periodic table would be neon. In order to achieve this electron configuration, sodium will lose 1 electron to become Na+. It now has the same electron configuration of neon. Note that this does not mean that it has the same properties as neon, nor that it has become neon. Recall that protons determine what element we have. Chlorine, on the other hand, has an electron configuration similar to argon. Chlorine will need to gain an electron in order to match the electron configuration of argon to become Cl-. Generalizing, we see that group 1 elements will always lose 1 electron to become +1 ions. Group 2 will lose 2 to become +2. Group 3 will lose 3 to become +3. Group 4 could lose or gain 4, so they rarely form ions. Group 5 will gain 3 to become -3 ions. Group 6 will gain 2 to become -2 ions. And group 7 will gain 1 to become -1 ions. The noble gases, as we know, generally do not form ions because they already have a full octet. Note that in the previous slide we only talked about S and P block atoms because these are the atoms that form predictable ions. Showing these charges again, we see that they can easily be predicted by their position on the periodic table. D block atoms, however, will form a variety of cations and do not follow the octet rule. This is due to the fact that they will lose their S electrons first, but then will also lose a few D electrons. There's no way to predict exactly how many D electrons will form. Therefore, copper, for instance, exists in 3 forms: copper +1 or copper 1, copper +2 or copper 2, and copper +3, copper 3. Notice we use a Roman numeral to indicate which form of copper we're dealing with. Ionic bonding occurs when electrons are transferred from a metal atom to a non-metal atom. Recall that metal atoms tend to lose electrons while non-metal atoms tend to gain electrons. So an ionic bond must contain a metal cation and a non-metal anion. This process is pictured here for the formation of NaCl. A sodium atom loses its 1 valence electron and transfers it to chlorine. Sodium has now become a positive ion with 8 valence electrons, and chlorine has become a negative ion with 8 valence electrons. The resulting electrostatic attraction between the positive and the negative ion results in an ionic bond. When an ionic solid forms, the ions will arrange themselves in a lattice to maximize positive and negative attractions, as seen in the diagram here. Notice that the purple positive ions will be surrounded by green negative ions on all sides. This repeating pattern is called a lattice. Also notice that there's no individual molecular unit for an ionic solid. It will expand in all directions depending on how many ions we have. Therefore, we can't use the term molecule to describe an ionic solid. Instead, we often use the term formula unit to describe the smallest ratio between ions in the compound. Ionic compounds are very stable due to the very, very strong electrostatic forces between closely packed oppositely charged ions. Recall that Coulomb's law tells us that as the distance between opposite charges decreases, the force of attraction between them increases. So let's consider the energetics of ionic bond formation. Looking again at the NaCl equation, here we see that we have a negative delta H, or a negative enthalpy change, for the formation of 1 mole of NaCl. Every time 1 mole of NaCl is formed directly from its elements, it releases 410.9 kilojoules. So what are the steps that go into this process? Well, first, sodium needs to lose an electron. This is an endothermic process. Chlorine needs to gain an electron, which is an exothermic process. The values describing these processes are the first ionization energy for sodium, which is 496 kilojoules per mole, and the electron affinity for chlorine, which is negative 349 kilojoules per mole. So it seems like overall this process should be endothermic, since we had to put in more energy to remove sodium's electron than was released when chlorine gained an electron. This doesn't make sense, since we've already seen that this is an exothermic process according to its delta H of formation. So there must be another factor at play. It turns out that ionic compounds are stable due to the positive and negative interactions of ions. The example above has not accounted for this interaction yet. So let's look at this interaction. We use the term lattice energy to describe the energy associated with the attractions between positive and negative ions. Lattice energy is usually defined as the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. However, I think it's more helpful to think of lattice energy as the energy released when 1 mole of ions comes together to form a compound. Lattice energy is essentially an indication of strength of interactions between ions. A larger lattice energy means that more energy was required to separate the ions, or, looking at it on the flip side, more energy was released when the ions came together. Looking at a particular example, it requires 788 kilojoules to separate 1 mole of NaCl. Reversing this equation, we see that that means that 788 kilojoules are released every time 1 mole of NaCl forms. You'll see values in the table to the right. These values must be determined mathematically. They cannot be determined experimentally. Now let's consider again the energetics of ionic bond formation with this new lattice energy in place. This is called the Born-Haber cycle. It describes the formation of an ionic compound. Let's look at each step. First, solid sodium is converted to gaseous sodium. That's an endothermic process. Then, our Cl2 is split into Cl, another endothermic process. Then our neutral sodium is converted to a sodium ion with the ionization energy of sodium, another endothermic process. Then chlorine is converted to a Cl- ion by gaining an electron, an exothermic process, the value of which is the electron affinity for chlorine. And finally, energy is released when Na plus and Cl- come together. This is the lattice energy of NaCl. So you'll notice the large lattice energy is what accounts for the overall exothermic process of the formation of NaCl. We have a series of endothermic processes, but this large exothermic process causes more energy to be released than was put in. Returning again to Coulomb's law dictates the size of the lattice energy. Recall the Coulomb's law equation. Q1 and Q2 are charges on the ions. So for sodium, Q would be +1. D is the distance between the center of the ions in nanometers. Therefore, lattice energy will increase as the magnitude of the charges on the ions increases and as their radii decreases. Put another way, ions with larger charges and smaller radii will have a larger lattice energy. Smaller radii allows the distance between the ions to be smaller. Looking at some data, here we see all +1 and -1 ions, so all of our Q values are 1 here. However, we also see that as our cations get smaller, our ions are able to get closer together, so distance decreases and lattice energy increases. Likewise, as our anions get smaller and smaller, our distance decreases and our lattice energy increases. Now that we've looked closely at ionic bonding, let's zoom out a bit and compare ionic bonding to covalent bonding, which we'll look at in the next video. It's important to realize that bonding lies on a continuum, from completely covalent to completely ionic, with lots of variation in between. Essentially, type of bonds depends on how equally or unequally the electrons are shared between the two atoms in the bond. Ionic bonds share so unequally that they're actually not even sharing electrons anymore. The electrons are actually transferred. One takes an electron from the other. Again, this usually occurs between a metal and a nonmetal, because metals give up electrons and nonmetals gain them. Covalent bonds, on the other hand, will share electrons. This sharing can be equal or unequal. The degree of equalness of sharing will determine how polar the bond is. These generally occur between two nonmetals. Here's a graphic showing this continuum. If we consider the electronegativity difference, or the difference in how attracted the electrons are to an atom, when the difference is 0, we have a fully covalent bond with no ionic character. As the difference gets larger and larger, our bond becomes more and more polar and increases in ionic character, until finally we have a very large difference, giving us a fully ionic bond, which is very low in covalent character and very high in ionic character. The important takeaway here is that bonds are generally not either ionic or covalent. They lie on a continuum. That brings us to the end of this video. Let's review our goals. First, we looked at ionic bond formation. Then we looked at some properties of ionic solids. We looked at the Born-Haber cycle to describe the energetics of ionic bond formation. And we learned how to predict the most common ion that an atom will form.